In this video, we're going to be looking at how to find the volume of solids of revolution. And before we get into our notes, I just want to give you kind of a visual of what's happening here when we find a solid of revolution. Let's say that we have this function, which is shown here as it is the square root of x. The region starts here at 0, and this point here is 9. We're going from 0 to 9. So I'm going to take this region, and what I'm going to do is rotate it around the x-axis, kind of leaving a trail behind, and it's going to form a solid. So watch as I drag this. You can see it kind of coming, like it's coming up out of the screen. And at this point, we've gone like maybe 180 degrees, a little bit further there. But you can kind of see that solid starting to form. I'll keep going. And unfortunately, on this applet, I'm going to have to stop before I make it all the way around, because if I keep going, I'm going to lose my dragging point behind that full screen button there. But hopefully you can see that we can take this region, this two-dimensional region that we start out with, and rotate it around. Internet's being slow. There we go. To create a solid. Now, if we go back to the original image, if you imagine a rectangle in here, and I wish I could draw on the screen. I can't do that. But imagine that we've got a rectangle. And if I take just that one rectangle and rotate it around, actually, let's do this. Let's say y equals 4. That'll give us a rectangle. So now I have a rectangle. If I rotate that rectangle around, hopefully you can see that what we get is a cylinder. And so when I go back to what I had graphed before, the square root of x, which I'm typing in as x to the 1/2. Imagine doing a Riemann sum here and making several rectangles to estimate this region, rotating all of those around. Each of those would make a cylinder. And so we could find the volume of all of those cylinders and add them together. And then what happens when we actually do an integral for this is that the number of cylinders becomes infinite, just like we used to do with area when the number of rectangles would become infinite. So let's talk about this with this example. We're going to sketch y equals x squared, which is going to look like this. Y equals 0, that's the x-axis, and x equals 2. So here's my region. I'm going to kind of shade it in. And what we're going to do is revolve it around the x-axis to create a solid. First thing I'm going to do is just kind of show you this rectangle idea that I'm talking about. If I draw in a rectangle like that we might use for a Riemann sum, I can usually, to draw these, the best way to start is to like do a reflection, which I've tried to do there, and then kind of make a rounded edge here. I will say this is not my greatest strength as a calculus teacher here, drawing these 3D images. But hopefully you can kind of see that as I rotate that rectangle around the axis, it would create a cylinder. And if I reflect, here we go, reflect my parabola, I can kind of, make a little oval here to show that circular nature. These are not easy to visualize. This is not easy to visualize, but hopefully if you can understand what's happening, we don't have to visualize it. We can just use the formula. If I were to slice off a piece of this solid, what would the area of a cross-section look like? Well, a cross-section would be a circle, because we're making these cylinders. Area of a circle, of course, is pi r squared. And in this case, if I use this rectangle I drew in to as a representation, what is the radius of the circle? Well, in this case, it would be our function, which is x squared. And so the area of this one circle that we have here would be pi r squared, but instead of r, I'm going to put in the x squared, and then we're going to square it. And the reason that the notes takes us through that is to get to this point, what would be the volume of I'm going to say just this one cylinder. Let's change this to, what would be the volume of one cylinder? Well, the volume of a cylinder, if you remember from geometry, is pi r squared times the height. And this pi r squared, we've already come up with that, pi x squared squared. And then my height, just like with area, is going to be delta x, this little height right here. And so if I take infinitely many of those cylinders, delta x becomes 0. Remember, as the number of rectangles goes to infinity, in this case, the number of cylinders would go to infinity, that delta x approaches 0, and that's how we end up with an integral. And so we're going to integrate from a to b. Our formula is going to be pi r squared. I'm using a capital R right here, just trust me for now, dx. Pi big R squared dx. And what this is, again, it just comes from the formula for volume of a cylinder, pi r squared times the height, where that height is the delta x or the dx. So let's look at an example. I'm going to start by sketching a quick graph. X plus 1 is going to look something like this. Y equals 0, x equals 0. So those are the axes. And then x equals 2. Here's 2. So this is our region. We want to rotate it around the x-axis. I'm going to try once again to draw a picture. Again, we don't have to have the picture because, in fact, let me do this one without the picture, and then I'll finish the picture in a moment. I'm going to draw in a rectangle. This is going to be your r. So we're going to have the integral from pi r, and notice r, the length of r is the function x plus 1 squared dx, pi r squared dx. Our limits here are going to be x numbers. We're starting at 0 and we're going to 2. Now, if I go ahead and finish my drawing over here, could draw in these little circles. You can kind of see it kind of looks like a squished megaphone, maybe, something like that. But really not necessary, as long as we understand if we draw in one of the rectangles, that's going to represent, the base of that rectangle is going to represent the radius of our cylinder. And still this distance down here on the x-axis is our delta x or our dx, which we know is the height of the cylinder. This question is going to be a little bit different because notice instead of going around the x-axis, we're going to go around the line y equals 2. So 3 minus x squared would look like this. It's crossing up here at 3. So y equals 2 is going to be here. X equals 0, that's the y-axis. And x equals 1, fortunately, it goes right there through that intersection point. So here's the region that we're rotating. I'm going to draw in a rectangle. Now this time it's going to be a little bit different, finding the length of our radius. Remember, this is going to give me the radius. The base of the rectangle is going to give me a radius. And kind of like we talked about with area, the length of your radius is going to be top minus bottom. Just like imagine that we had, let me just give you a quick example. Let's say this is 5, 4, 3, 2. So we've got a little number line, and let's say that I had that this was my rectangle. And I would say, how long is this? Well, you could look at it and say, oh, well, that's 3 because I can do 5 minus 2, and that gives me 3. So we take whatever the highest is, whatever the lowest is, we subtract them. That tells me how long it is. So in this case, the highest point on my rectangle is going to be that top function, the parabola, 3 minus x squared. And then the bottom of the rectangle, that's on the axis that we're rotating around, which is 2. top minus bottom, that gives me my radius. And then once I have the radius, I'm going to integrate pi r squared dx. Following our formula up here, pi r squared dx, pi r squared dx, remembering that r is going to be top minus bottom. And then I'm going to put my limits on here. They should be x numbers because we're doing dx. I'm starting at 0 and going to 1. Now notice on both of these, I'm not actually evaluating the integral, and I should have said that up here on the previous example. I'm just setting this integral up. That's really where I want us to focus when we're doing this section. It's just on how to set up these integrals. And let's not get too bogged down with actually evaluating the integral. All right, let's look at example 4. This one's going to be a little bit different because notice this time we're revolving around the line x equals 1. And x equals 1 is going to be a vertical line. And so the rotation here, the revolution, is going to be just a little bit different. So I'm going to sketch this graph for us. 2 minus y squared. That's going to be like a sideways parabola like this. X equals 2 minus y squared. And x equals 1. Vertical line like this. And so we're going to take this region, and that's what's going to be rotated around x equals 1. And this is our axis of rotation. So again, I'm going to draw in that representative rectangle into my region. Notice this time it's going horizontally. It's going perpendicular to that vertical line that we're rotating around. And this means that when I finally end up doing my integral, it needs to be a dy. If I'm rotating around a vertical axis, that means I'm doing this with respect to y. My integral is going to be a dy integral. Still, the base of this rectangle is your radius, but in this case, we can't do top minus bottom because it's going sideways. We're going to do right minus left because right's going to be the highest value, left is going to be the lower value. And so with this particular example, the right side of my rectangle, what forms that boundary is going to be our equation 2 minus y squared minus the left side of my rectangle, well, that's stopping at that vertical line x equals 1. And so my equation here, pi r 2 minus y squared minus 1 squared, this time dy instead of dx. And then, and this is important, since this is a y, my limits on the integral here, they should be y numbers as well, which means I need to know what these intersection points are. And just looking at it right now, I can't tell. But remember, when you can't tell what the intersection points are, what you can do is set these two functions, or well, these aren't functions, set these two equations equal to each other. So let me block this off. So I've got 2 minus y squared. I want to know when that equals 1. I'm going to add y squared over to this side, subtract 1. Y squared is equal to 1. So that means that y equals plus or minus 1. And so my lowest y value here is, of course, going to be the negative 1. And then my highest y value, positive 1. All right, let's do one more. Notice that my initial starting equation here is the same sideways parabola, 2, but this time I'm rotating around x equals negative 2. So I'm going to go, let's see, 1 right here, negative 2. There's my axis of rotation. Let me draw in my parabola, sideways parabola. Okay, not exactly symmetrical, but we'll pretend like it is. All right, so here's the region that we would rotate. And again, notice on these, I'm not drawing the picture of our rotated region. We could draw it every time, but we don't have to. All we really need is that representative rectangle drawn into the region to help us figure out the radius of the cylinders that we're making when we rotate the region. So again, in this case, we're going to do right minus left. If I look at the right edge of this rectangle, what's forming that boundary is our equation 2 minus y squared minus whatever's forming the boundary on the left. That would be the vertical line -2. So that's my radius. My volume is going to equal pi r, which is all of that. I'm changing it to +2 minus -2 is +2 squared. This is a dy because because our rectangle is horizontal. It's perpendicular to a vertical axis that we're rotating around, so it's going to be dy. And again, we need these intersection points, and I didn't really save myself room. I'll do that over here. 2 minus y squared equals -2. So if I add y squared over here and add 2 over there, we get 4. And so y is ±2. And so that means that our lowest value here, the y coordinate is -2. And up here, my y coordinate is +2. All right, hopefully those give you some good idea about how to set these up, set up these integrals. In some of these questions down here in the homework, it is going to ask you to go ahead and integrate, but these are polynomials, should be fairly simple to integrate when it's asking you to actually evaluate the integral. And then hopefully on some of them, we can just leave it just with the integral, set up the integral, and don't get bogged down too much in actually integrating and finding the answer. I want us to focus on how to set up those volume integrals.